This video, we're going to look at the material biconditional. So this is the characteristic truth table for it. Um, it is true if both of the components have the same truth value and false if they have different truth values. So if they're both true, it's true. If they're both false, it's true. And then if one is true and the other is false, then it's false. The symbol that we use for it is this right here. It's called a triple bar. Um, In other systems, this will sometimes be represented with a double arrow, like an arrow pointing in both directions, but we don't use that in SL, right? What we use in SL is the triple bar. Um, in North America, the standard phrase for representing the biconditional is just if and only if, right? So like you can have your dessert, or you can have dessert if and only if you eat your broccoli. And I should maybe say, right, in North America, when people are speaking precisely, which isn't very often, um, arguably the most common way that people represent the biconditional in North America is actually with if, where when what they're thinking is a biconditional, but what they actually say is if. But that's something we're not going to worry about, right? This gets into like sort of really tricky questions about when to interpret, people as uttering biconditionals instead of conditionals. We're just not going to worry about that. Um, so the way that the textbook paraphrases the biconditional is with, right, if and only if underlined. So you can have dessert if and only if you eat your broccoli. And here when this occurs in a complex sentence, you do need parentheses to indicate where the biconditional begins and ends, because there's nothing, the textbook paraphrasing method doesn't have anything at the beginning. So it doesn't have anything to tell you where the beginning is. You will need parentheses for that. Um, you may want to shorten this to IFF instead of writing that whole phrase out. So you can have dessert if you eat your broccoli. Now, in British English, the standard phrase for the biconditional is just in case. So you can have dessert just in case you eat your broccoli. This we would paraphrase as you can have dessert if and only if you eat your broccoli. And this is something that you hear sometimes in Canada, partly because of British influence on Canadian English. Um, and particularly in academia, you'll hear academics use just in case in this sense a lot, because I mean in general in among North American academics there's a lot of influence from British English specifically. So you will hear this in university courses and things like this. You may actually come across this. Normally in North America, what just in case means is because it might, right? So, we would normally say something like, I'll wear a jacket just in case it gets cold. This means I'll wear a jacket because it might get cold. Um, because the because here is it's a logical connective, right? It connects to two component sentences. I'll wear a jacket and it might get cold, but it's not truth functional. It says that there's a connection between these two. It says that it might get cold is a reason for this sentence, I'll wear a jacket. Because it's not truth functional, we can't symbolize this in SL, right? This is not something that we can actually represent. The closest that we can get to symbolizing this sentence in SL is actually with and, right? I'll wear a jacket and it might get cold, where we just assert these two things that have been asserted and we ignore the fact that there's a claim that there's this connection between them, right? Where this one here is the reason that's given for this. That's just stuff that we can't represent in uh, in um, in SL. So that's the way that the biconditional works. The last thing that I want to talk about in this video is so we've gone through all of the different connectives in SL and looked at the definitions of the truth functions for all of those different connectives. And so what I want to talk about briefly here is an alternative way of defining the truth functions, which is sort of interesting. So What we do for this definition is instead of having T for true and F for false, we're going to let one represent true and then we let zero represent false. And then we'll have this here, V of P. This is this represents the truth value of P, right? So that is the value that sentence P takes. So then once we're using these numbers, right, one and zero to represent the truth values true and false, then we can define the truth values of the connectives as, or the truth functions for the connectives as follows, right? So or here, or is just max, right? It picks out whichever of these it takes whichever of these is the truest, right? Or it takes the truest of the two, whichever their value is. So if either of them is true, then it just returns true. And only if both of them are zero will it give you a value of zero, right? And is min. It takes the least true of them. So if either one of them is zero, then it returns zero. And only if both of them are one will it return a value of one. Not what it does is it flips the values, right? So one becomes zero, zero becomes one. We can represent that with one minus the value of the sentence. For the conditional, this is something we didn't really talk about, but the material conditional is actually equivalent to not Q or P. So that's the simplest way to define it in this system. Is that's the value of not P, right? One minus the value of P, and then you just take max one minus the value of P and the value of Q. Then for the biconditional, um, remember that the biconditional is true if the two have the same truth value, and it's false if they have different truth values. So what we do is we take the absolute value of their difference. And if they have different truth values, then that's going to be one. And if they have the same truth value, that's going to be zero. That's the reverse of what we want. So we just subtract that from one. So, and then we'll end up with this is going to be one if the difference between their truth values is the absolute value, but the difference between the truth values is zero, and it will be zero if the difference between the truth values is one. So that's an alternative way of thinking about how the truth functions in SL work.